So let's get some solution sets to the problems that we did today, or rather, a few days ago. So I have my handy TI-83 Plus calculator that some poor hapless student left on my desk. So if you're missing one, you might want to talk to me so that you can get it back so that it's not pilfered and used for lousy physics videos on YouTube. So force of gravity, and let's remember force of gravity and weight mean exactly the same thing, and the formula for weight is mg, where this of course is 9.8 meters per second squared. So let's start off simple. What's the weight of a 60 kilogram person? Weight is 60 times 9.8, and again 60 kilograms is mass, so just a little quick note here. Mass is in kilograms, weight is in newtons. So when we go ahead and get this mass, it's going to be 9.8 times 60. Oh, joy of joys, 588 newtons, if I have that right. Yes, beautiful. So these calculations, I was expecting them to be extremely straightforward, but that assumes that you feel completely comfortable with the units. So when we say, what is the mass of a 100 Newton backpack, the 100 newtons is its weight, and the mass is what we're trying to solve for. So we use W equals mg. That means 100 equals m times 9.8. We divide and solve for m, and we end up getting 10.2 kilograms. Okay, and continuing on, we have the force of gravity on a ball is 45 newtons, and we want to know its mass. So once again, I think a lot of people, when they do weight problems, they assume that weight is some kind of unit conversion for mass, and it's actually not. So we always switch the terms force of gravity and weight around, even though they mean the same thing, to constantly remind you that weight is a force. It's the effect that Earth has on an object. So again, we have weight equals mg, so that means 45 equals m times 9.8. And we go ahead, simplify that, and we're going to get that the mass is 4.6 kilograms. Now here, the acceleration on gravity on the moon is 1.6 meters per second squared. We want to know what the weight of 350 kilogram rocks is on the moon. So weight of the rock due to the moon equals the mass of the rock times gravity on the moon. So that's going to be 350 times 1.6. And that's what I'm saying is on the moon actually applies less force to the rock. Now, what's that weight of the rock on the Earth? That's going to be 350 times 9.8. And when we go ahead and get that, we actually end up getting 3,430 newtons. So in other words, it's easier to deadlift rocks on the moon than it is on Earth. Now, continuing on, problem number 5. A person has a weight of 285 newtons, so the weight of the mass on Mars is 285, and the mass of the person is 75 kilograms, and we want to know what gravity is on Mars. Newtons. So we have this situation. Sorry, I actually had to pause for a second, got interrupted, lost my train of thought. So we have the weight and the mass of 75 kilograms, and we want to know what the acceleration due to gravity is on Mars. So again, that's going to be weight divided by mass, weight on Mars divided by mass. Notice the mass doesn't change on Mars, it's still the same. So 285 divided by 75 gives me 3.8 meters per second squared. On Earth, the weight is simply 75 times 9.8. And of course, that's 735 newtons. All right. Now, we got the force of gravity on a 1,200 kilogram robot. We want to know what that is if we have this acceleration. So once again, weight is mass times gravity on Saturn. The weight of the robot, the weight of the mass on Saturn equals the mass times the gravity on Saturn. So that's going to be weight, mass, because of Saturn, equals 1,200 times 8.96. So when we go ahead and get that, we get 10,752 newtons. Excellent. So that's it for the weight problems. And again, be really clear. Remember, weight is in newtons, mass is in kilograms. Weight means the force of gravity. Mass is the amount of stuff in an object, and we're going to tighten up that definition a little bit later next week. We did problem 1, so the solution to this is in video 2. So you need to kind of watch video 2 to get the solution to this first problem. Let's go ahead and take a look at the second problem. So here, it says a block weighing over 300 newtons is moved at constant speed over a horizontal frictional surface by a force of 50 newtons applied parallel to the surface. Let's get a force diagram of this block. So we've got the normal on the mass due to the surface, the weight of the mass due to the earth. We have this applied force, and we have a kinetic friction acting on the object. Right? Now, what's the coefficient of kinetic friction? So we're moving at constant speed in a straight line. This tells us that the force is balanced. So what that means is this force balance, and the normal and the weight balance. So let's go ahead and actually write those facts down. So I know the force applied equals the kinetic friction. And since I apply a force of 50 newtons, it says applied 50 newtons. So that means the kinetic friction is going to be 50 newtons. Now, I also know that in the vertical direction the force is balanced. So the normal force equals the weight. Now, here's a trick. They tell me the block weighs 300 newtons, and I know that from the units. That's a unit of force. So what that tells me is I know the normal force is 300, and so I use my coefficient of friction equation, my friction equation. Friction is fun, is how some people say it. I don't say it that way. Mr. Farrell likes to, though. So we have 50 equals mu kinetic times 300. And so we solve for mu kinetic. That's the coefficient of friction. So coefficient of friction always means that squiggly letter mu, and it's kinetic, so it gets the subscript k. And so we end up getting 0.17 for our coefficient. No units on that. So here, I want to add one word to this sentence because I think people got confused on this. It says a 50 kilogram crate. I'm going to add the word initially resting, because here's what happens. Since we have a coefficient of kinetic friction, what happens is that this box, let me just make a note here, does not stay still for the problem. This box then moves. And I don't know if that's at constant speed. I don't know that. We're going to go find that out. So draw a force diagram to represent the situation. Here we go. I got a normal on the mass due to the surface. I got the weight on the mass due to the earth. I apply a force, and I have a friction force going the opposite way. Now, what's the force of gravity? That's the weight. Okay, so I got 50 kilograms times 9.8, and I'm going to get 490 newtons of weight. The normal force, well, I do know in the vertical direction the forces do balance. So what I'm going to end up getting is the normal force equals the weight, and that means it's 490 newtons. So to get the kinetic friction, I cannot assume that these balance. I don't know, because I don't know if it's moving at constant speed. I have no idea. They never told me. See, here in this problem, they told me constant speed, so I know. Where else? I know they did here. Again, in problem 5, they tell me constant speed. So I know I'm good there too, right here, constant speed. But in problem 3, they don't tell me, so I can't assume. The way to calculate, so what they really mean is predict what the friction should be if this is the coefficient. So that's Fk equals 0.15 times 490. And that's going to give me 73.5 newtons. Right. Now, what is the difference between the friction force and the applied force? I don't mean the conceptual difference. I mean the difference, like subtract the two and find out. So the force applied minus the friction, that's going to be 100 minus 73.5, and that's going to give me, when I actually get it, 26.5 newtons. Okay, so this is actually the situation that we're going to be doing our lab on next week. We have unbalanced forces. And what we're going to learn about next week is, what does this mean? Okay, what's going to actually happen? Now there's a little hint of what should happen in the next problem that we do. So it says in the situation above, the coefficient of static friction is 0.25. Is the 100 Newton force sufficient to cause the crate to accelerate? Let's find out. So first we draw a free body diagram. We got the normal on the mass due to the surface, weight of the mass due to the earth. We apply a force, and we have the friction force acting on the crate. Now, what needs to happen is, just like in the lab, the force applied had to overcome the static friction. So let's calculate what that, let's predict what that static friction should be using the coefficient. So that's going to be 0.25 times 490. And that tells me that I've got to overcome a static friction of 122.5 newtons. How much force did I apply? I applied 100 newtons. The maximum static is 122.5. So no, I can't overcome friction. All right, finally, this last problem, let me just see how I'm doing on time here. Good, plenty of time. So 36 Newton force as he pulls 50 Newton sled at a constant speed. Let's draw the force diagram for the sled. Man, you guys got to be sick of this one by now. We got the normal, we got the weight, we got the applied force, and we got the friction force, and it's kinetic. Now, what's the normal force? This is nice. It's 52 newtons. Notice they give me newtons. It's already weight. It's already weight. You believe that? What's the kinetic friction? Friction is mu times normal. Mu kinetic times normal. So that means I'm going to actually get here, since it's a constant speed, 36 equals mu kinetic times 52. And that gives me 0.69 for my coefficient. Now, if the mu kinetic is 0.12, what force do I need to pull the sled at constant velocity? Well, that means that the force applied would have to equal the force of kinetic. Let's get this new force of kinetic friction then. That'll be 0.12 times the normal force of 52 newtons. And so I get 6.24 newtons of force. Wonderful. So that's it for that one. Now, I want to talk a little bit now in this next section about what we're going to be doing on Monday. And so what that means is notes for Monday. I want to review something really quickly. I've got about 3 minutes to do it, so I'm going to have to be quick. So I wanted to do a quick review of some trig stuff we did from last semester. So suppose I have a force pointing at 30 degrees and it has a magnitude of 5 newtons. If you remember, we can split this force into two parts, an x component and a y component. And what I want to do now is actually do that for this force right here. If you remember, fx equals 5 times cosine of 30, and fy equals 5 times sine of 30. So when we actually calculate that in our calculators, we're getting the y component of the force is 2.5 newtons, and the x component is 4.33 newtons. So here's why we are interested in this. We've been doing horizontal forces like this. What we're interested now is in moving to forces that move at an angle like this. And we only know how to balance horizontal and vertical forces, so what we're going to be doing next week is practicing what happens when we split forces into vertical and horizontal parts.